Okay, so this is the review for Unit 3. Number 1, given the following table of values, use finite differences to determine if the graph is linear, quadratic, exponential, or neither. Okay, explain your answer. So for finite differences, what we're going to do is we're going to go up the y column and we're going to subtract these numbers. So in other words, we're going to go like 33 minus 17. I get 16. Okay, 17 minus 9. I get 6. I get 8. Yeah, 9 minus 5. Okay, so, 9 minus 5 is 4. Okay, I'm not going to write these out anymore. 5 minus 3 is 2. 3 minus 2 is just 1. Okay, so it's not linear because the first differences are not constant. So not linear. Okay, so let's go ahead to second differences. 16 minus 8 is 8. 8 minus 4, 4 minus 2, and 2 minus 1. Okay, so this is not quadratic either. So what we're going to do is we're going to do ratios now. Okay, and we're going to do ratios of the y column. So we have 33 over 17. We're going to have 17 over 9. We're going to have 9 over 5. 5 over 3, 3 over 2. Okay, so I get 1.94, 1.88, okay, 9 over 5 gives us 1.8. Okay, 5 over 3, 1.67, 1.5. Okay, these are clearly not the same. Okay, so if we're taking a look at these, we would say that they are not exponential. However, there's like another way of determining if this is exponential, if that a value is not, the initial value is not 1, is actually to do the ratios of the first differences. So if we went up the first differences column and we went 16 over 8, we'd get 2. 8 over 4, we'd get 2. 4 over 2, we'd get 2. And 2 over 1, we'd get 2. So based on the ratios of the y column, we wouldn't be able to determine if it's exponential. And we would have said neither, but because of the ratios of the first differences column are equal, this is exponential. Okay, number 2, classify the following equation as linear, quadratic, exponential, or neither. Okay, so when we have y equals 6 minus 3x squared, this tells us that it's quadratic. I'm going to put a Q. When our exponent is our x value, our variables in our exponent, it's exponential. Okay, if we were to expand this out, we would get an x squared. So this is quadratic. We said that the base of an exponential function cannot be negative, so this is actually neither. And then this is linear, okay, because it's just x to the exponent 1. Okay, number 3, a bacterial colony has the initial number of 1,000 cells, so this is A0. The number of cells doubles every hour, so this is the basis 2. The model that represents this exponential growth is, okay, so I would say the initial value is 1,000, so it's going to be one of either A or C. Okay, the initial value is not 2 or 4. Now, we double every hour, so our doubling period's 2, so we're going to have a base of 2, so I'm going to go with A. Okay, number 4, there are currently 36 lions in the wildlife sanctuary in Africa. Okay, so this is going to be our starting value, A0. The population of lions is increasing at a rate of 4.5% per year. So when we're talking about percentages, we would say increasing would start at 100%, and that's if they had the exact same amount of lions every single year, and we're going to add 4.5%. So we're at 104.5. Okay, as a decimal, this is 1.045. This is going to be our base. So write an equation that represents the scenario, then use the equation to determine the population 15 years from now. So this is the time. Okay, for population, we're going to round to the nearest whole number. So the amount at time t equals 36, which is our start, 1.045 to the exponent t. And we're going to figure out the amount at time 15 years from now. So all we're going to do is sub in that 15 to the exponent. Okay, and then we take our calculator and we do 36 times 1.045 to the exponent 15. Remember, do not multiply these two bases before you do the exponent. We have to follow exponent laws. So I get 69.6. Why don't we round to 70? Okay, therefore, 15 years from now, there will be 70 lions. Okay, 5. You buy a computer for $3,000, so that's the initial amount. Its value depreciates by 5% a year. So when we talk about 8% a year. When we talk about depreciation, we talk about subtracting. So our initial amount is 100% of the value, and we're going to subtract 8%. So we get 92%. So our decimal for our base is going to be 0.92. How much is your computer worth after 3 years? So the amount at time t equals, let's write an equation first. Initial amount is 3,000, and then every year after that, it's only going to be 92% of the previous year. So decimal 92 to the exponent t. The question asks, how valuable will it be after 3 years? Okay, so go ahead and put this in your calculator, 0.92 to the exponent 3 times 3,000. I get 2336.06. 2336.06. Okay, and remember, money goes to 2 decimals, therefore, its value will be 2336.06. Okay, number 6. In a laboratory, they were testing a certain bacteria. They started with 50 bacteria. So this is going to be our A0, and they notice it doubles, so our base is 2, every 3.5 hours. So if it doubles every 3.5 hours, we're going to have some time over 3.5. How many will exist after 1 day? So 1 day, if we convert 1 day into hours, it would be 24 hours. Okay, so I'm going to fit it here. The amount of time t is going to be 50 times 2 to the exponent t over 3.5. So if we were to sub in 24, we'd be kind of asking how many half-life or doubling lives are there in 24 hours. So if we did like the 24 divided by 3.5, it's a really not nice number. So I'm personally going to substitute this entire exponent into my calculator, and I'm going to make sure that I put brackets around this exponent so that that exponent stays together. Okay, and I get 5796.6. So I'm going to just round 5797. Okay, so therefore there will be 5797 bacteria after 1 day. Okay, number 7. Match each equation to its corresponding graphs. So we have 3 equations, 3 graphs. I'm just taking a look at the equations, and what sticks out to me is that this is the only equation where we have a base that is between 0 and 1, which means that this one's going to be decreasing. When looking at our graphs, there's only one decreasing graph, so number 1 matches up with B. Okay, now taking a look at this graph, both have a scale on the y-axis by 40. So 20 would be here and then 40. So what we can simply do is just find the y-intercept. So y equals, this is for A, 22 to the 0. So the initial value for A is going to be 20. This one's going to match up with A. And if we actually algebraically did this one, 2, 4 to the 0, our y-intercept is going to be 2, which is way down here, which matches up with C. Okay, number 8, a radioactive material has a half-life, so the base is going to be 1/2, of 10 days. So we're going to have some number of time over 10. And the initial mass of 2,000 milligrams, so A0. Write the equation relating the mass of the radioactive material M in milligrams to the time T in days. So this is going to be a little bit different. We're going to have the mass at time T is going to be like the initial mass, so mass naught, B to the T over D. That's going to be, it's the exact same equation except for we're writing M instead of A. So let's write an equation, okay? So the initial mass is 2,000, the base is 1/2, and we get T over 10. B says, use the equation to determine the amount of radioactive material after 40 days. So in other words, we're kind of asking, how many half-lives do we have in 40 days? Well, we would have 40 over 10, which is 4. Okay, so do the exponent first. So 0.5 to the exponent 4, you're going to get 0.0625, and then multiply it by 2,000. Okay, I get 125, and that's in milligrams. So therefore, after 40 days, there is 125 milligrams remaining. Okay, number 9, the following table of values models an exponential function in the form y equals ab to the x. So we can see the transformations on here is just this initial stretch, okay, the vertical stretch by a factor of a. There's no reflections, there's no shifts or translations, okay, up, down, left, or right. State the equation. So because we're in the form y equals b to the x, our initial value is right here. It's when we have a y-intercept. So our initial, a, b, and the x. So our initial value is 3, and then our base is going to be our ratios up, like if we did the ratio column. Okay, so 21 divided by 3, I get 7. Okay, if you divide up the rest of these, you're still going to get 7. So I get 3, 7 to the exponent x. Okay, b, the initial value here is 2, so y equals 2. I'm going to get some value to the exponent x. So remember, we have to go up the y column for the ratios. So what is 2 divided by 32? Well, it's 1 over 16. Okay, make sure that you don't just say, oh, 32 divided by 2, because that's a way easier calculation, right? 16, it's 1 over 16. Okay, and if you keep going up this y column, you're still going to get 1 over 16. Okay, so in here I have I'm counting the boxes, 1, 2, 3, 4. So all of these go up by 5 each time. So my initial value is 5. Okay, and then for example, if we're going up the y, like if we have 1 and then 2 in the x and y, 1, 2, 3, and then we have 15, 45, 135. If we were to divide these, we would get 3. So 45 divided by 15 is 3. I get 3 to the x. You can put the x in here or the x outside. Doesn't matter. Okay, number 10. Describe the transformations or series of transformations that must be applied to the base function y equals 2 to the x to obtain each given function. Okay, so A is going to be this equation here. We have a vertical stretch. I'm going to put VS by a factor of 2. So I'm going to short form it, but make sure that you're doing the long form on a test. Okay, right 1, up 7. Okay, for B, we have this one. Okay, we have a vertical compression by a factor of 1/2, left 2, down 2. Okay, and then for C, we have this one here. We have reflection in the x-axis. Okay, the 3 is a vertical stretch by a factor of 3. We have to factor this, so we get 2x plus 4 as the exponent. That means we have a horizontal compression by a factor of 1/2, and we're moving to the left 4. And then we're going up 5. Okay, number 11, use the shortcut method to create a rough sketch for each of the following in order to say, okay, whether the function is increasing or decreasing. So let's look at A. So 3 to the x we know is going to increase to the right, and there's no reflections, so this just increases. Okay, number 2, the equation of the horizontal asymptote. This moves up 4. So our horizontal asymptote is y equals 4. Okay, the y-intercept, we can just sub in 3 to the 0 plus 4. This goes to a 1. Our y-intercept is 5. Okay, our domain is XER because it's an exponential function, and our range is YER such that y is greater than 4, which is our asymptote. Okay, so for B, we have our base graph is 2 to the x, which is going to look like this. Now the stretch doesn't matter, it's going to look the same, it's just going to be stretched. But we're going to reflect it in the x-axis, which is going to make it look like this. Then we're going to move it down 2, which is going to make it look like this at -2. I shouldn't put that there, that looks like a y-intercept. Let's go -2 here. Okay, so is it increasing or decreasing? This is now decreasing because we reflected it. The horizontal asymptote is y equals -2. It's this number right here. The y-intercept, let's go ahead and sub in 0. So I get -7 minus 2, I get -9. Okay, so I get XER for the domain and YER such that y is less than -9. Sorry, less than -2. -9 was y-intercept. -2 is the horizontal asymptote. Okay, and the last one. Our base graph is 1/4, so it looks like this. Stretch does nothing to it. Moving left and right does really nothing to it. But moving down 5 moves this horizontal asymptote to -5. Okay, so we can see that this is decreasing. The asymptote is y equals -5. If we were to plug in, so 2 1/4 to the 0 plus 1 minus 5. If we plugged in 0 to that x, we get 2 times 1/4, which is 1/2 minus 5. I get -4/5. Or sorry, 4.5. Okay, the domain is XER and the range is YER such that Y is greater than the asymptote, which is -5. Okay, number 12, for the function f of x equals 2, 3 to the -1/2 x minus 1, minus 2, sketch it using mapping notations, list any asymptotes. So this is our original. And if we can take a look at the exponent here, we need to factor out this -1/2. And that's just a common factor, okay? So I get 2 base 3 to the exponent -1/2, but now I'm going to bracket x plus 2. -1/2. Yep, that's good. So our original mapping from our original, so our base graph is 3 to the x, okay? So we're going to have -1, 0, 1 and the horizontal asymptote. So then for the y's, we're going to have 1/3, 0. It's not 0. I always do 0, but it's 1. And then 3, and the horizontal asymptote is y equals 0. Okay, so we're going to have a reflection in the y-axis, horizontal stretch, so this is actually a 2, and we're going to move left 2, so -2, and then for the y's we have 2y minus 2. So sub in -1 we get 2 minus 2, 0, sub in 0 I get -2, sub in 1 I get -4. Okay, 2 over 3 minus 2. I think it's -1 1/3. 2 over 3 minus 2. Yeah, -4 over 3. Let's just put that as a decimal. -1.3. Okay, this is 2 minus 2, which is 0, and then 6 minus 2, which is 4. Okay, our horizontal asymptote is this number right here, which is -2. So if we were to graph this, I would first graph the horizontal asymptote, which is y equals -2. And then I know I'm going to graph points at 0, -2, and -4. And then this is -1, -2, -3, -4. So 0, -1 1/3, -2 and 0, and -4 and, 4 is up here. Okay, so it's going to look like that. And then you can label that f of x. Okay, number 13, let f of x equals 1/4 to the x and g of x equals this function, so -2 of the function x minus 3 plus 4. So describe the transformations. This is a reflection in the x-axis. Okay, this is a vertical stretch by a factor of 2, sorry. This is right 3, up 4. Okay, so this is A. So our equation, when we substitute, basically we're putting the function like right here. So we leave f of x, we can call it g of x actually. Let's call this g of x equals -2, and I'm going to put the function here, 1/4, and then this x minus 3 goes to where the x would be, and then plus 4. Okay, the mapping would originate from the function 1/4. So I would get 4, it's not 0. Do that every time, 1/4, and then horizontal asymptote is at y equals 0. Our mapping notation would be -2y plus 4. That's the easiest. It's the front and the back on the y's. Now we're going to the right 3, so x plus 3. Okay, negative 1 plus 3, 0 plus 3, 1 plus 3. Now, negative 2 times 4 is negative 8 plus 4 is negative 4. Negative 2 plus 4 is 2. And then negative 2 over a quarter, like times a quarter, is negative a half plus 4 is 3.5. Okay, horizontal asymptote y equals 4. So if we were to graph this, I would graph the horizontal asymptote at y equals 4. 1, 2, 3, 4. And then I'm going to go okay, all of these are by ones. So 2 comma negative 4, 3 comma 2, and then 4 comma 3.5. And this is our g at x.